Hello and welcome back. Year 13 integration revision. We are now on examples 116 to 127. I lost track of which lecture we're on. I haven't done this for a little while, so I thought I'll come back and give you a little bit of a continuation to what we're doing up to now. Okay, let's start. I got a lesson in literally half an hour, so I better finish this lecture before my bell rings. So let's start very quickly. There's a lot of trig in this particular page. We are now exam standard practically. By the time we're hitting this kind of integrations, we should be ready for an exam or perhaps for a mock. So I won't be showing as many workings as I have done in the past. So this particular integral is clearly integration by parts, product of two quantities, different families, and also the sec squared is very special, some kind of differential. So I'm going to differentiate the x and I'm going to integrate the sec squared. This of course goes to 1 and a tan of x differentiates to sec squared. So when I'm doing the workings in this particular fashion, the answer is always the product of that, which is x tan x minus the integral of this particular diagonal. So that's minus the integral of tan of x dx. And I'm going to put some results up here for today. This is in the formula booklet, but you might be asked to prove this particular result. The integral of tan of x is in fact the log of sec x plus c. You might write it as minus log cos. It's exactly the same. So I'm going to use it here without anything else to say. So that's x tan x minus the log of sec x plus c. So that's question 116. We're going into question 117, which is the integral of cosec of 2x cot of 2x dx. Okay, trig again, double angle, but there's double angle on both, so that could have been just cosec x cot x. So is this something special? The answer is yes, it is. I'm going to write another thing up here. The differential of cosec of x is minus cosec x cot x. This is again the formula booklet and the differentiation. So this is an exact differential. It's just that it's got a chain of 2 from the 2x on both. So that's going to be, first of all, a cosec of 2x that needs to be differentiated. I need a minus according to that, and I also need a half in front of it because of the 2x to make it work. So that's 117. 118, I think I can also fit it on this particular page. 118 is the integral of tan squared x sec squared x dx. Just making sure I copied it correctly. How do we do something like that? Of course, your first gut feeling is to switch into sines and cosines. I've not really tried to go to sines and cosines. I'm going to be entirely honest with you because I can see the answer to this one. But try substitution. I want to say something about substitution, okay? How do you know what substitution to use? Well, there's a couple of things here. Either try the substitution u is equal to sec x, either the substitution u is equal to tan x. Become more exotic if you prefer it to go by u is equal to, I don't know, tan squared of x. And then you can say perhaps, look, either I found something that works or this doesn't work, or maybe I'm making a mistake, and at least you will know you can go safely to another technique. This particular one, for the record, the substitution u is equal to tan x will actually work in about 3 lines. But this is very special because, of course, the differential of a tan, any power, doesn't matter there whether it was squared, cubed to the power of a half, to the power of 7 over 2, as long as we got a sec squared next to it, is integrable. Because this is a higher power of tan, so tan cubed, with the third in front of it. Why is that? Because if I differentiate this, I'm going to get 3 times the third, which of course is 1. And then I'm going to have the tan reducing the power by 1 to tan squared, times is the differential of a tan, which of course is a sec squared of x, which is exactly what we got up there. Okay, you're welcome, of course, to try the substitution, but if you don't see how this is done. Okay, next question is question 119. That's actually quite quick as well. Very simple by the looks of things. Loads of trig on this particular page. I don't know if that's a good thing or a bad thing. I prefer trig to sometimes tedious stuff. Number 119 is the integral of sine 2x cosec of just x. Well, quite clearly here we need to break the double angle. Like the previous one, we had 2x and 2x. There's no way this will integrate as it is. So switch into sines and cosines by breaking this particular double angle identity times the 1 over sine dx. Your sines, of course, will cancel, and this will give you a integral of 2 cos of x dx, 2 cos x, and this, of course, is going to be a sine differentiates to plus, so also good, 2 sine x plus a constant. I just want to say I've switched into a new type of pen, and I don't know if this is good enough for the videos. It's a little bit thinner and not as dark as the ones I was using before. But by the way, if my videos are not very clear, because sometimes I have the same problem depending on what device I'm on and whether the internet connection is very good, please, they're all recorded in high definition, and therefore go on the settings on the side of the video and up the quality to the maximum quality that your connection and your device allows, because I've noticed that can be sometimes a bit of a problem. Okay, number 120, more trig. Integral of 2 cos x minus 3 sine x all squared dx. Of course, we're not going to increase the power by 1, and because that's, of course, not linear. This is just the squaring of the bracket. We've done loads of this in the past. So 4 cos squared x minus 12 sine x cos x. Sorry, I'm going a little bit fast today. I'm almost certain, because this student always arrives early, that the bell is going to go before I finish this lecture. Okay, so this is now what we got. This is, of course, the 6 lots of the sine of 2x. What I'm going to do with this, I have identities. I'm going to write them on the side. I've used them several times. They come from the cos double angle. They used to integrate sine squared of x and cos squared of x. Identical, half and half, half and half. Both have a cos of 2x, cos 2x, cos 2x. The sine has the minus and the cos has the plus. So for this particular one, I'm not quite going to replace both of them. I'm going to do an in-between step just to show you. I'm going to take 4 cos squared from there and 4 sine squared from there to make a 4. That will still leave me 5 lots of sine squared from here. Plus, of course, no, plus, minus, rather. That's the minus 6 lots of the sine of 2x dx. Then I'm going to use, of course, the identity for 5 sine squared. So it's 5 bracket half minus half cos 2x, which I wrote down there in red, minus 6 lots of the sine of 2x dx. Do a bit of a tidy. 6 plus 2.5 is 6.5, so that's 13 over 2. 13 over 2 minus 5 over 2 cos of 2x minus 6 sine of 2x dx. And of course, the integration of that is simple. 13 over 2x. To get a cos 2x, I need to differentiate a sine of 2x. Sine differentiates to a plus, so the minus must have been there from the beginning. Divide by a further 2 from the chain, 5/4. And to get the sine of 2x, I need to differentiate a cos of 2x. Cos differentiates to a minus, so the minus must have been a plus to start with. It changed from the differentiation, and the times 2, and if you divide by 2, 3 cos 2x plus c. And just to check that I haven't done anything silly, just checking the answer for this one. 13 over 2x, I didn't put an equals there, very bad. 13 over 2x minus 5 quarters sine 2x plus 3 cos 2x plus c. So it's all good. We're going quite fast, and I hope we're all following in there. I need to clear the board. So the next one is actually okay again. So 121, but it's still more trig. 121 is the integral of the sine of x plus the tan of x over the cos of x dx. What I'm going to do with this, switch into sines and cosines possibly, but I prefer to split my fraction. So this will give me now sine over cos, which is a tan, and this is good because that's the standard thing that's in the formula booklet, and tan over cos plus tan x over cos x. What I want to do with that, switch into sines and cosines perhaps? The answer is no. If you look carefully at this particular one, I'm going to write the cos at the top as a sec. So I'm going to write it as tan x, that was there, times the cos next to it, but now it's called sec. And the reason for that is, I don't know if I have space to put it up there, is another perfect differential. The differential of sec, I hope it's visible at this, that low on the board. D by dx of sec is in fact sec x tan x. So this is an exact differential what I've got up there. And of course, this comes from the log of sec x up here, and this comes from a sec of x plus c. Okay, this result again is in the formula booklet, but under differentiation. Okay, 122. This particular one, yes, we can just fit it here. It's we've done things like that already, or similar. 1 plus sine x, 1 plus sine x over cos squared x dx. Let's think about what technique is involved for something like that. And I just want to show you something that some of the bright students often go through when they see this particular integral, which is it's good to actually think of it, but it's not effective, unfortunately. They say, oh, I can see things there. And I say to them, what do you see? I'm just don't writing the integral there. They're just saying, okay, look, 1 plus sine x, cos squared I can write as 1 minus sine squared of x, and then this is a difference of squares, so I can write as 1 minus sine x, 1 plus sine x. Let's ignore, because in the integral there, blah blah blah, there's no limits, so let's ignore that we can potentially might be dividing or by 0, so we can cancel that. And then they have this kind of thing and say, oh, that's simpler now. See if I can integrate it. And now the voice goes a little bit like that. And you say, how do I integrate that? And the answer is not very easily. In fact, if you were given this particular integral, you're going to have to walk backwards and do exactly what this student would have done, times top and bottom by 1 plus sine x, to get it to that, and then move in the opposite direction that we're about to move now in order to integrate it. So I don't know if you followed what some very bright students, and I'm not actually criticizing, that's actually good to be thinking laterally and experimenting and trying things. This particular one is, of course, splitting your fraction. Immediately, I can say to myself, look, 1 over cos squared is a sec squared of x, which I know is the differential of a tan, which I know I can do any time of the day. The question is, what's the rest? Sine of x over cos squared of x. This is another special form which you need to remember how you do things like that. It can be done a couple of different ways. It can even be done by reverse chain rule if you're very bright, but I'm not going to show you this one here. I'm going to write sec squared of x, and I'm going to write this as sine x over cos x, and the other cos from the cos squared, I'm going to write it as 1 over cos of x. And of course, the reason I'm doing this is because that is, of course, sec squared x which integrates, and this is a tan with a sec next to it. Did I write this result up there perhaps earlier on for you? There you go. Bottom of the board there, the differential of a sec is sec tan. So this is now my sec tan, and there's a sec squared. And of course, this comes now from tan x differentiates to sec squared, plus a sec of x differentiates to sec tan. Okay, that was number 122. We're going to 123. That is also very easy. Once you see it, of course, is e to the sine x cos x dx. Okay, how do we integrate something like that? Of course, this is actually quite tricky because most people in the very beginning, when they're looking at something like this, they will say, well, it's the integration by parts, isn't it? Because it's a product of two different families, mathematical families, exponential times a trig. It can only be integration by parts. The answer is not quite. This doesn't actually work because it's actually not how it was produced. It's one of the rare cases, and you need to keep it in mind. What would you do after that? There's not a lot of things you can do after that, but substitutions. I said earlier on, please do not be scared of substitution. Try different things. U is equal to cos x. You will find if you do that, it doesn't work. If you do U is equal to sine x, you will find that this is in fact 3 lines. So this in fact works. And for those who can actually see ahead, and we are exam standard, and we will probably be laughing at this, we'll say, look, this is just simply e to the sine x. If I differentiate that, I'm going to get e to the sine x back times the differential of its argument, which is just the cos x, which I'm saying in there. And therefore, there's nothing else to write. That is your answer. And if you use a substitution, that's the answer that you're going to get. Okay, 124, a little bit lengthy, but not difficult. And it's, again, it has trig. But there's not a trig technique involved in this one. 1, 2, 4. I'm just checking out. I didn't miss anything. 1, 2, 2, 1, 2, 3, 1, 2, 4. Is the integral of x squared times the sine of x dx. We should all know what this is. We've done loads of those. This is, in fact, the integration by parts. We should also know it's a double integration by parts from experience, perhaps, because this is x squared in there. And I'm going to go and do it straight away. I'm going to differentiate the x squared, and I'm going to integrate the sine of x. X squared differentiates to 2x. Sine comes from the differentiation of a cos. Cos differentiates to minus sine, so it's a minus at the front. And the way I do my integration by parts is the product of this. So minus x squared cos x minus the integral of, always minus the integral of, the product of this diagonal, which is minus 2x cos x dx. And of course, immediately sort out your minuses in there. Do not leave live minuses lying around, because the question will simply eat you at some point. And if it was a cos there, it would be even worse. The sine is not actually that bad. So let's rewrite the beginning. And I need integration by parts again for this integral, because this doesn't integrate. So another little grid, 2x and cos x, differentiate the 2x to integrating this, so that comes as a sine differentiates to plus, so that's all good. And that's going to give me the product of that, which is 2x sine x minus the integral of the product of this diagonal, which is 2 sine x dx, close square bracket. Here we're lucky because, of course, the square bracket has a plus. The cos is the nasty one. If it was, as I said earlier on, x squared cos, it'd be minuses and more minuses, and it'll be very, very painful. Plus 2x sine x minus the integral of 2 sine x dx. And this one we can actually finish it off now. Minus x squared, the cos of x, plus 2x sine of x. Okay, this one comes from a cos. Cos differentiates to a minus, and I can treat this minus as being part of the differentiation, so it starts as a plus. And of course, no change, so I have to account for this too. And of course, this is the answer. Again, let me just check, just in case, because I'm rushing at the moment and I'm a little bit error prone. Just check the answer. Which number is that? 1, 2, 4. Minus x squared x, 2x sine x plus 2 cos x. Yeah, that's all good. Number 125. We can fit it in there. I think it's the only non trig in the page. 125 is of course the integral of 2x plus 1 all to the power of 3. How do we do that? Maybe cube the bracket. Okay, I'm only joking. We can actually cube it. It's not that difficult, and we get the answer. Just people will be laughing at us if we do something like this. This is just of the form ax plus b to some power. So it's a linear adjustment. Increase the power by 1, so to the power of 4. Adjust your constant now. Times 4 from the 4 times 2 from the chain is 8. Needs 1/8 in front of it, plus c, and this is done. 126 and 127. Okay, clear the board, make some room. 126, we're returning, unfortunately, back into trig. So much trig on this particular set of questions today. I don't mind trig. That's 126. I prefer it. Oh, my cat wants to go out as well. Give me a second. Give me a second. I've got 2 questions to go, okay? Yes. Please don't make a lot of noise now. I'm under pressure here. Albert is coming. The cat is meowing. I'm losing my mind here. Okay, dx. Didn't we do that today? I think we did. It was just different powers and it was written differently. You can try substitutions. As I said, do not be shy. Try u is equal to cos x, u is equal to tan x. Try your luck. In fact, u is equal to tan x will in fact work. But that of course does not require substitution, if you can say it. It's tan to the 4 of x, and this cos squared, write it next to the tan as a sec squared of x. We've done exactly the same question, only I think it was a tan squared in there. This is a higher power of tan because sec squared of x is the derivative of the tan. So if we start as tan to the 5 and we differentiate it, we're going to get 5 coming to the front. Okay, let's write it here. The tan will go to the 4 times the differential of the tan, which is sec squared. It's exactly what we got in there, apart from this 5. Let's kill the 5. And we're done. Okay, that's 126. And the last question, oh no, not trig, but I'd rather be doing 3 questions of trig, but than something like this. Is it hard? No, it's just annoyingly tedious. All right, let me just move that to the middle of the board. If I had known this was the last one, I would have actually put it somewhere in the beginning or in the middle. I don't want to be finishing with this. Just an anticlimax, really. Plus 5 over 2 minus x bracket 2x minus 1 all squared dx. Okay, what technique is involved in this one is kind of obvious. Brackets on the denominator is partial fractions, isn't it? Just annoying because we got repeated factors and halves and ugly things on the top. It's not improper, by the way, because that's of course x and another x squared there, x cubed at the bottom, x squared on the top. Okay, let's do the partial fraction. I'm going to show full workings. It's the last one, so let's give him some time. My brain anyway at the moment is not working very well, so if I do cover-ups I might make mistakes. Okay, identically equal to something over 2 minus x plus something over 2x minus 1 all squared. And possibly, that might be there or might not be there, 2x minus 1. Okay, so equate tops, 4x squared minus 6x plus 5 is identical to a. From this bit here, you need to take the full 2x minus 1 all squared. The b has this item, so you need to take the other bracket. b, 2 minus x. And the c needs to take the 2 minus x, but he also needs to take one more of these brackets because it's not squared there. 2x minus 1. Okay, let's try some sensible numbers. If x is equal to 2, and 2 because this bracket and this bracket will kill all of this. So we go 4, 16. So we go 16 minus 12 plus 5 is equal to, gone, 2, 4, 3, 9. 9a, 2, 4, 9 is equal to 9a. And of course, use your calculator, yeah? A is equal to 1. We're going to put now x is equal to a half, trying to get rid of that and that. X is equal to a half, quarter, 4, 1 minus 3 over 2 plus 5. And then we've got, this is gone, 2 take away, 2 take away our, where is it? 2 take away half is 3 over 2, so that's 3 over 2 b. So we go 5, 6, 4 and a half. So we're gonna have 9 over 2 is equal to 3 over 2b. So my b must be equal to, is it 3 or is it 2 there? 2's 9 divided by 3 is 3. Am I making a mistake in there? I don't like that 3 in there. Just bear with me for a second. X is equal to a half. Quarter times 4 is 1. We're putting a half. Sorry, that's not 3 over 2. That's actually a 3. I put a quarter in there. Okay, just bear with me for a second. Just correcting my workings in there. Half of 6 is 3 plus 5. So it's going to be 5, 6, 3. So that's a 3. Okay, I'm rushing, and this is what happens when you're rushing, of course. 1.5 times b, so b must be equal to 2, so that looks a little bit better. And the last one, we can put any number really, because there's no more good numbers to use. So x is equal to 0. Okay, so this is now gone. 5, 0, so that's 1. I'm going to put the a is equal to whatever it is later. X is 0, so plus 2b. And x is 0 here. 2 times minus 1 minus 2c. So we go 5 is equal to, my a is 1. My b is 4. And therefore, c will in fact be equal to 0. So I'm returning to my integral. And this is what we got now. We got the a, which is 1 over 2 minus x, and the b was 2 over 2 minus 1 all squared, and this of course is not there. The c was 0. Dx. Careful, because this is not a log, so the best way to do this, don't rewrite it necessarily, but write either wherever you got your space above it or below it. 2 bracket 2x minus 1 to the power of minus 2, because it is a linear adjustment, and all we have to do is just finish it off, and hopefully we've done it correctly. So this is a log, so it's obviously the log of mod 2 minus x. We have a minus from the chain. You can actually swap this if you want, x minus 2, because it's modded in there. And for this, increase the power by 1 to the minus 1. Now differentiate it. Minus 1 times 2 is minus 2. 2 divided by minus 2 is minus plus c. And let's check this. And there you go. My student has just arrived. He's actually correct. And I'm going to leave you here and open the door. Who's laughing now?